Welcome to this lecture series in number theory. In this lecture, we'll discuss Fermat's little theorem, and let's just recall one thing, which is the notion of the order of an element. So suppose we are given two relatively prime integers, and let's say both are non-zero. Then we know that there exists a positive integer k such that this congruence holds, right? And the smallest such k is called the order of A modulo P. Order of A modulo N. So order of A modulo N is the smallest such k. Okay, great. And one more thing, one more property of order is that if, let's say, D is the order of A modulo N, and suppose this congruence holds, so what's a good exponent? Let's say M. Suppose this happens for some M, and here M also doesn't have to be positive. M could be any integer, where we have to again recall or remember that negative powers means appropriate power of the inverse. So A to the power minus 3 means you take the inverse of A modulo N and then raise it to the power 3. We discussed this. Okay, great. So if this happens, then we know that the order divides M. So we saw this was just a consequence of division with remainder theorem and the definition of the order. And with that, let us proceed. Some problems for practice. And now let us get started. So to illustrate the main idea in the proof of Fermat's little theorem, we haven't even stated the theorem, but whatever is the main content of the proof, let me illustrate that in a small example, just like we did for Wilson's theorem. And then we'll look at the formal statement and the proof. So I have a prime P, which is defined as equal to 7. But of course, the true statement is about an arbitrary prime. So fix this prime P, and suppose X is some integer. Doesn't matter which integer. Let's just say it's just something that is not divisible by P. So clearly X is not divisible by 7. And now consider the following numbers. Consider the numbers X, 2X, 3X, 4X, 5X, 6X. Yeah. So what did we do? We have all these remainders modulo 7. These are all the remainders modulo 7 except the 0 remainder. Right? Except for 0, these are all the possible remainders when you divide something by 7. So we have done is we have scaled the integer x by those remainders. But what we will do is, we are not interested in these numbers. We will reduce them modulo 7. So what happens if you reduce x modulo 7, meaning just write the remainder of x when you divide it by 7, you get 2. What about 2x? 2x is 18, or you can be a little more clever, but whatever. 2x is 18, and the remainder that 18 leaves modulo 7 is 4. 3x, you will find that it is 6. 4x, 4 9s are 36, and 7 5s are 35, so this leaves a remainder of 1 modulo 7. 5x, you will get a 3, and 6x, you will get 5, I think, yeah. So what are we witnessing? We are witnessing all the possible non-zero remainders that you can get when you divide something by 7 in some messed up order. We are not seeing it in the same usual order. It's just that they are jumbled up. So if we multiply all of these numbers and take the remainder modulo 7, we will get the same thing when we multiply all these numbers and take the remainder modulo 7. So from this observation, what we conclude is the product x times 2x times 3x modulo 7 is same as 1 times 2 times 3 times 4 times 5 times 6. Right? Once again, the remainders of these numbers modulo 7 are in some order 1, 2, 3, 4, 5, 6. We are not saying that x leaves the remainder of 1. It doesn't. It leaves the remainder of 2. It's just that some permutation has happened, but when you're taking product, it doesn't matter in which order you're producting things. Commutativity of product. Whatever. So we have this congruence, and therefore we get x to the power 6 times 1 times 2 times 3 times 4 and so on, which is same as saying x to the power 6 times 6 factorial. Now here one could use Wilson's theorem, but there is no need. So what we get is that 7 divides this number. Right? This should be clear because this is congruent to that modulo 7. So the difference is divisible by 7, and that is what I have written. But note that 6 factorial is relatively prime to 7. 7 is a prime, not dividing anything in the product. So this implies 7 divides x to the 6 minus 1. So what have we seen? At least for this particular x, we have proven this congruence holds. But this argument, this little fact is true, that the permutation property, whatever you want to call it, this will be true whenever x is not divisible by 7. If x were divisible by 7, then all these remainders would be 0. That would be silly. But as long as x is not divisible by 7, this permutation property will hold, and the same conclusion will also therefore hold. Fermat's little theorem just generalizes this, and the reasoning remains the same. So let's do it. So we have a prime. We have some integer not divisible by p. We want to show this. In the previous example, p was 7, x was 9. Here everything is generalized. So we'll just repeat the reasoning. In fact, I encourage you to do it yourself. That is much, much better than looking at what I'm going to do. So define this map, and this is just bookkeeping. Define this map f from 1 to p minus 1. How do we define it? Just send a to a times x, but then there is a problem. A times x may not even land here, right? So just like in the previous page, we will record only the remainder modulo p. So I'll write a mod p here, and maybe I'll write the full thing. So we'll map it to the remainder obtained when ax is divided by p. That's what I mean, but I will just express that by writing, or I might have expressed this by writing as ax and then a mod p. Not a great notation, but it's fine. Alright, and here's the thing. We'll show that f is a bijection. So claim, and you must be able to see where this is going. Just like in the previous page, we are going to show that all the things that you obtain here, are all the things here. So f is bijective is what we are going to do, and then product things out and whatever. So let's show why is f a bijection. Enough to show that it is an injection. Enough to show that f is an injection. This is because the domain and the target are of the same size. So injectivity automatically implies bijectivity. But if f of a equals f of b, then what does that mean? It means the remainder obtained when ax is divided by p is same as the remainder obtained when bx is divided by p. One thing I did not say is that the remainder obtained when ax is divided by p is here. It is not outside this, because if were it outside this, the remainder must be 0, because that's the only remainder that is not seen here. But can this leave the remainder of 0 when divided by p? No, because if that were the case, p would divide this guy, which would mean p divides at least one of them, but that is not true by hypothesis. A is certainly not divisible by p because it is coming from this set, and x is not divisible by p by hypothesis. So this was a legitimate map. Whatever, so if fa is equal to fb, we are trying to show that a is equal to b because we are trying to show the injectivity of f. So why is a equals to b? Because fa equals fb means ax and bx leave the same remainder when divided by p, which in the language of modular arithmetic is this. So just take note of this step, and now this implies that a minus b times x is divisible by p, which implies p divides, what have I written, a minus b times x, which implies p divides a minus b, which implies a equals b. Now why does that happen? So first of all, why does this implication hold? Because x is not divisible by p. We have done this so many times. So why does the divisibility of the difference of a and b imply this equality? Well, that's because a and b are in this range. If you take the difference of two things here, you cannot suddenly get 0. Whatever, so I'm sure you follow all these steps. So the injectivity and hence the bijectivity of f has been established. And thus, just like in the example that we saw, thus the product of all the possible non-zero remainders is same as up to remainders modulo p, meaning the product of all the non-zero remainders modulo p is congruent to, in fact, I can write an equality here, right, which implies the left side is p minus 1 factorial, and here I'll write a congruence. Right, and that gives us the rest is something that you see, but I'll write it. Right, so I've done just basic modular arithmetic. From here, I took took this thing to the left side. We get this, and then this guy is relatively prime to p, so we can drop it. So we get that, and hence we get that. All right, so that proves Fermat's little theorem. Interestingly, Fermat didn't supply a proof when he announced this result to a friend in a letter as he usually would. I think he never gave any proofs. He just threw out challenges. And then later, Euler provided the first proof, at least he published the first proof. But later, I think it was found that Leibniz had already almost had the same proof. So yeah, some interesting history behind this. Anyway, so this is also referred to as Fermat's little theorem. It's just a very simple consequence of the thing that we just saw. If p is a prime and x is any integer, this time we're not insisting that it is not divisible by p, it is any integer, then this congruence holds. So there are two possibilities. Either x is divisible by p, in which case this is trivial. The other case is x is not divisible by p, in which case we have this congruence. And if you just multiply by x on both sides, you get the desired. So that's it. So I'll just write this as an exercise, even though I have explained why. Exercise. Okay. Let's see a simple computation, how Fermat's little theorem facilitates evaluation of remainders modulo primes. So here we have this humongous number, and we want to find its remainder when divided by 59. And 59 is a prime. So for simplicity of notation, I will write p as 59. And we are interested in 5 to the power 119, so we will slowly build up to it. By Fermat's little theorem, we know that 5 to the power 59 minus 1 is congruent to 1 modulo p. P is again 59, as I said. So that means 5 to the power 58 is congruent to 1 modulo p. Square both sides. We get 5 to the power 1/16 is congruent to 1 modulo p. And that gives us, we multiply by 5 cube on both sides to get this, which implies the left hand side, which is the thing that we were interested in, is congruent to 125, but 125 is congruent to 9 modulo p. I'll write a 59 here. So this is just a computation. So it helps. This was much faster than we would do like we did in our very, very early lectures. There it was slower, still pretty fast. And the fear was gone. After modular arithmetic, this kind of question invokes no fear. Before that, it does. All right. So here is a simple fact about order of an element that we can deduce using Fermat's little theorem, at least when the divisor is a prime. So fix a prime p, and suppose we have an integer x which is not divisible by p. Then we know that the order of this element exists modulo p. However, we are able to say that the order will divide p minus 1. So it narrows down this guy to not be just some arbitrary number. We have some information about it, and some non-trivial information about it. And this will be very useful in the next lecture. Okay, so why is this true? Well, by Fermat's little theorem, we know that this congruence holds. And by what we recalled in the beginning, immediately from that, we see that order of x modulo p divides this number. That's it. So yeah, something to be noted. And now let's look at some puzzles and applications. So here is a nice puzzle. This will not, I encourage you to pause the video and think about it. What I'm trying to convey from this is that n doesn't have to be prime in order for this to hold. So what does the puzzle ask us to do? We are given some positive integer a. So this a is different from that a. We are given some positive integer a. We want to find a composite number n such that this happens. So for each a, there is a composite number n which kind of witnesses the same equation, same congruence equation as we saw in the statement of Fermat's little theorem, or the alternate version of it. So that's the kind of thing that I wanted to convey, that there is some sort of, non-characterizing fact that I want to convey. Anyway, forget about that. So let's just take this as a puzzle. And let me show you why this is true. Of course, I'm assuming you have spent enough time on it. So if A itself were composite, then this is very clear. If A were composite, then just take n as A and we are done. Right? Because then n would be a composite number and this congruence is trivially true. So assume A is a prime. And we'll change notation and call it P for psychological reasons. Okay, and here is something that I don't want to spend too much time explaining. Consider this number, P to the power what should I write? Just give me a second. Yeah, so let Q be some divisor of, so let Q be a prime divisor of this number. Correct? Just something, I mean, we'll see why we have done this. So clearly P divides this guy. What we are claiming is that we claim, and even before the claim, I'll say that let n be equal to something. So let n is P times Q, and we claim that this congruence holds. This will finish the proof, because P is nothing but A and n is clearly composite. Okay? So why does this happen? Well, to prove this, we just need to show that P divides this difference and Q divides this difference. So the proof is, this is equivalent to showing that just think about why, because what is this congruence? This is just saying P to the n minus P is divisible by n, which is to say that P to the n minus P is divisible by P times Q. But when is something divisible by P times Q, where P and Q are different primes? It's when that number is divisible individually by P and Q. Because P and Q are actually relatively prime. That's the important thing there. This is the clubbing property or something, whatever. Yeah. So this is what we want to show. This much is clear. This part is clear. This is clear, of course. So we are interested in that thing. So want to show, or maybe I'll just start like this. So now P to the power n, this is by definition P to the power PQ, and which I will write like this: P to the power Q to the power P. And by Fermat, this is congruent to P to the power P modulo Q. Right? Because by Fermat, this is congruent to P, and we are just exponentiating it by the same number. So this is where we used Fermat's little theorem. Okay, and this is congruent to P. This is congruent to P modulo Q simply because Q was the divisor. Q was chosen as a divisor of this guy. So this is congruent to that. So we have shown that P to the n is congruent to P modulo Q, and that finishes the thing. This was the only thing left, and we are done. So this was sort of the main idea, that you start here and I don't know how to explain it. You mess around and you find it. There may be many other ways to prove this particular result, but this is what I was able to manage. Okay. Now this is another very interesting puzzle. It says that if n is any positive integer, at least 2, then this congruence, I mean, what we are saying is that this congruence cannot happen. This just simply cannot happen. Very interesting. Unclear why. Okay, and I again encourage you to pause the video and worry about it. And the proof technique that we'll see will be very interesting. So let's see. So if n is prime, then we are done. By Fermat. Why? Because if n is prime, then 2 to the n is congruent to 2 modulo n. Immediately by the another version of Fermat. So we may assume that n is not a prime. And well, what is the simplest non-trivial case to try now? Either you take n as a prime power, or you take n as product of two different primes. Let's see what happens if n is the product of two different primes. We are just exploring how to prove that in that case, right? So This is just for understanding. So say, I'll write it in a separate color. So now say n is p times q, where p and q are primes, and they are different. So let's see how we would do this puzzle in this particular case. Okay. Right, let me think. Right, so 2 to the power n would be equal to 2 to the power pq, and that is equal to 2 to the power p to the power q, which is congruent to 2 to the power q modulo p. Right, because by Fermat, 2 to the p is congruent to 2 modulo p. We are assuming that p is an odd prime, because if p were equal to 2, then clearly this cannot hold. If n is divisible by 2, then this simply cannot hold. So we may assume that p and q are odd primes. Okay, fine. So for the sake of a contradiction, assume that this happens. Assume that this is true. That is, this is true. But this shows then that 2 to the power pq, or rather 2 to the power q, is congruent to 1 modulo p. Right, so I hope you see this. This congruence and this, or rather this congruence, these two congruences together give us this. Okay, so I'll write this one separately. Right, so this and that together imply that. Well, what does that mean? So if d is the order of 2 modulo p, because p is an odd prime, p is relatively prime to 2, so this is the legitimate thing. So what we see is that then d divides q, and we already knew that d divides p minus 1. This was generally true. I mean, the fact that d divides p minus 1 is a general fact. Why do we have this? Because of this congruence. So we have these two things, but there are two possibilities of order now. If d divides q, then d is either 1 or q. If d is 1, then we have a problem, because order of 2 being 1 means that the prime is equal to 1. So that's not going to work. That's not a prime. So therefore, d must be equal to q. So this implies that d must be equal to q. So therefore, we get that q divides p minus 1. Since d is equal to q and d divides p minus 1, we get q divides p minus 1. But this should already be, unsettling. Because what does this say? This says that q is lesser than p in particular. Right? But by the same reasoning, we did not, p was just arbitrary. The role of p and the role of q are not different. We did our reasoning for p and obtained that q is less than p. We can do the same reasoning by flipping the roles of p and q. We will get p is less than q. So that's a contradiction. Yeah, so I hope this reasoning is clear. Okay. Fine. What if n were a prime power? So this is one special case. This doesn't resolve the question in its generality. This is a special case. Similarly, let's do another special case. Suppose n was a prime power. This is even easier. So now if 2 to the power n, so there is no if. Yeah, okay, let's say that. So if 2 to the power n is congruent to 1 modulo n, then in particular 2 to the n is congruent to 1 modulo p, which implies 2 to the power p to the power k is congruent to 1 modulo p, but 2 to the power p to the power k, and here maybe I'll put a bracket just for clarity. So this is equal to 2 to the power p to the power p to the power p up to k times. Difficult to write. So my point is that we already know, but by Fermat, 2 to the power p to the power k is congruent to 2 modulo p. This is by Fermat. For instance, if k were equal to 2, let me just explain there. If k were equal to 2, then what is this? This is equal to 2 to the power p to the power p. But the thing inside is congruent to 2 modulo p, so this is congruent to 2 to the power p, which again is congruent to 2 modulo p. And I'm just saying that no matter what thing you write here, instead of a 2, you can write a k, doesn't matter. We still have this. So these two congruences say that 2 is congruent to 1 modulo p, which is not true. So yeah, so that settles this puzzle in these two special cases, when n is the product of two primes or n is a prime power. From here you can do the general thing. These two, the ideas that are here and the idea that is here, together, if you combine them, you can do it for any n. Clearly we have already done it for a prime by Fermat. You can do it for arbitrary n. So that's an exercise, and with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.